Hi, I'm Jiang, a PhD student in Tsinghua University, and today I'm gonna present our paper named A Divergence-Free Mixture Model for Multiphase Fluids. My co-authors are Li Chengfeng from Swansea University, Deng from King's College London, and Hu Shiming also from Tsinghua. In this work, we present a novel mixture model that is divergence-free and improves both efficiency and accuracy of multiphase fluid simulation. Our work is implemented with SPH method, but should also be compatible with Eulerian approach. Now let's start from some background of multiphase fluid simulation. When simulating mixture of multiphase fluids like water and oil, or maybe alcohol, one can certainly simulate each phase with different sets of particles, and couple them together with boundary conditions, but that costs a lot of computation and is hard to implement as well, especially when the fluids are partially or fully mixable, where it is hard to even define a boundary. So another efficient approach is to use a mixture model, simulating the mixture as a single-phase fluid with a mixture velocity, and the phases are described as volume fractions. Like in this picture, a single particle carries multiple phases, and the movement of each phase is described with their relative velocity to the mixture, known as drift velocity. Then we need to only solve one set of equations for the mixture, and the drift velocity can be directly solved from a constitutive model. This greatly saves computation and is also easy to implement. The question is, how to properly define the mixture velocity? A natural thought is, we can define the mixture velocity as the velocity of mass center of a fluid particle weighted by mass fractions. This velocity, however, is not inherently divergence-free, even if all the phases are incompressible. We can see from the second equation that its divergence corresponds to the local density change of the mixture. And when the phases have different densities, the mixture's density is changing when phases have relative motion, so this is not zero. And this has two drawbacks. First, we cannot use the incompressible solvers like IISPH or DFSPH, so both the efficiency and stability is limited. Besides, if we advect the particles with this velocity, the volume of particles are actually changing, and the previous method neglected this effect, and the particle is scaled back to its original volume, and the mass loss of different phases are also different. For single-phase fluid, this is not a problem, but here it breaks the mass conservation. So is there a way to make the mixture velocity divergence-free so that we can both increase the efficiency and also conserve the mass? The answer is yes. We start from the continuity equation of phase K. The change of mass corresponds to the divergence of the flux. Assuming all the phases are incompressible, we drop the rho and have this formulation. Adding up all the phases, we have a divergence of some term that equals to 0. This indicates that a better choice is to use the sum of the velocity of each phase multiplied by its volume fraction. This is the volume-weighted mixture velocity. If we build our model upon this velocity, then we will have a divergence-free condition, which means the incompressible solvers can be used, and there is also no need to worry about the volume change and mass conservation. This is the main contribution of our work. Here is some comparison between our method to the previous method, and we can see the previous method suffers from some artificial color change due to the mass change, and our method conserves the mass well. Now I'll talk about our mixture model. The simulation procedure consists of two parts. The first one is solving the mixture momentum equation, and the second is to compute drift velocity and the phase advection. The first part is almost the same as a single-phase solver, and the second part is the unique part of a multiphase solver. This is the momentum equation. As we can see, the right-hand side contains several terms that is similar to those in the single-phase equation. The first term is the pressure, the second is gravity, and the third is a tensor term including viscosity, turbulent stress, and interface momentum tensor. The fourth is the interface drag force. The pressure, gravity, and the viscosity are defined similar to those in single-phase fluid. We can write the first term with mixture density, so that it is closer to the single-phase pressure term, except for factor gamma. According to this equation, we can use the pressure projection to enforce divergence-free condition. Please check the paper for the detail. After solving the momentum equation, we come to the phase advection, or the phase exchange between particles. Let's start again from the continuity equation of phase k. We define the drift velocity as phase velocity minus mixture velocity. We can substitute this into the first equation and get the material derivative of the volume fraction of phase k. In SPH method, this is used to update the volume fraction carried by the particles. Note that we have two equations. The first says that drift velocities multiplied by volume fractions should add up to 0. This is a constraint the constitutive model for drift velocity must obey. This also leads to the second equation, which guarantees the volume fractions always add up to 1, and the particle's volume is never changed. The last piece we need now is the formulation of the drift velocity. Since the derivation is pretty long, we leave it to our paper and directly give the result. We assume the relative motion between phases are small, and the local equilibrium is reached at every moment. This assumption is reasonable for most liquid mixture and most liquid particle suspension system, and the drift velocity can be computed from a drag force model. The first term is separation due to the inertial difference or the density difference, and the second term is diffusion due to the turbulent fluctuation. So the two terms are of opposite directions, and their relative strongness decides whether the phases are mixing or unmixing. And the volume fraction update and the drag force term is listed here for completeness. In this example, the three phases have different densities, and the gear's motion makes them together. When gears stop, the phases tend to separate back into layers. The SPH implementation is quite straightforward. As for explicit time stepping, using weakly compressible SPH, the pressure term is discretized in a symmetrical form like this, with an additional gamma. The existence of gamma does make the formulation a little less symmetric, but does not introduce observable problem. The tau dm term can be discretized as shown here, and the other two tensors can be replaced by an artificial viscosity, since implementing a physically meaningful viscosity model is normally an overkill for the applications shown here. The phase advection is symmetrically discretized here to ensure the mass conservation during the phase exchange. As we can see, the two terms, either the separation or the diffusion, can be seen as an accumulation of pairwise fluxes between particles. And finally, we give an outline to our RISPH implementation. The simulation loop starts from a normal single-phase solving procedure. We estimate particle densities, predict velocity, and compute DII. Then we predict particle density, compute AII, and do RISPH iteration to get the pressure and enforce the divergence-free condition. Then we update particle position and velocity. Then we just compute the drift velocity and the phase diffusion. This example shows the coupling between liquids and elastoplastic solid. This example shows an elastoplastic duck dissolving into water. And this example shows the dissolving of granular material into water. When dealing with high density ratio between phases, our method handles up to 100, but is still unable to handle extremely high cases like 1000. As a conclusion, we have proposed a divergence-free mixture model using a volume-weighted mixture velocity. Our approach improves both the efficiency and stability and achieves mass conservation automatically, where the error is controlled below 0.01%. However, there are still some limitations. Our method still cannot handle arbitrarily large density ratio between phases, and we also need to clamp out some negative volume fractions due to the time discretization and the numerical error. And that's all for my presentation here. Thank you for your attention.